We are currently deploying a massive interconnected physical network across the country. But unlike heavily monitored power plants of the past, this new grid lives in the dark corners of hotel lots, curbsides, and empty parking structures. In a traditional gas station, you have bright lights, staff, and cameras. EV charging stations are often the opposite, uniquely isolated, unlocked, and frequently unguarded. This isolation is a problem because these stations contain a valuable commodity. Inside the charging cables is a dense tangle of raw copper wire, a metal currently seeing a surge in global demand. Thieves target the heavy cables that transfer power to the vehicle. A standard direct current fast charger cable contains an outer protective sheath wrapped around 3 thick internal conduits packed with this copper. Combining high-value global commodities with zero security environments has effectively turned an essential green energy initiative into an unprotected resource cache. To see the impact of these systematic attacks on a local grid, we can look at the data from Seattle, Washington. Between March 2023 and January 2024, the city's public utility, Seattle City Light, reported that criminals targeted and disabled 8 of its 13 direct current fast chargers. Replacing a severed cable cost the utility approximately $2,500, a steep direct financial burden for the municipality. Replacing the hardware is only the initial burden. The structural consequence of these outages is the charging desert, vast geographic zones where power becomes entirely unavailable for EV drivers. A single incident of localized vandalism alters the city's infrastructure map, creating immediate blind spots in the regional transportation network. Extraction is rarely clean. To get to the copper core, thieves often burn away the rubber or plastic coatings, damaging the internal electrical systems in the process. This leaves behind dangerous physical hazards. The cut copper wires have jagged, sharp edges that can cause severe lacerations to maintenance crews or the public. There is also a significant risk of electrocution. Damaged, improperly grounded cables may still be attached to a live electric current, turning a broken charger into a live wire hazard. Adding an electrical fire risk to locations filled with EVs creates a compound danger, as the lithium batteries in these vehicles pose their own specific fire risks when exposed to high heat or sparks. A compromised charging node ceases to be simple broken machinery, becoming an active, volatile hazard zone. The national network is fragile. 1 in 5 U.S. stations fails to work reliably. Copper theft multiplies this unreliability, accelerating the spread of charging deserts and leaving hundreds of miles between working plugs. This creates severe range anxiety, forcing drivers into long, inefficient detours to reach a single power source. There is an economic penalty as well. A scarcity of usable stations drives up the pricing at the few chargers that remain operational. This scarcity traps the driver, making routine commuting physically precarious and financially punishing. Displaced EV traffic funnels toward the few surviving stations, concentrating vehicle demand into a handful of operational nodes. This bottleneck requires those residual stations to pull an outsized proportion of power to handle the sudden concentrated load. This artificial spike typically occurs during peak commuting hours, the exact time when the local electrical grid is already under its highest pressure. The sudden heavy draw from these overloaded chargers strains the regional electrical distribution system, stressing transformers and substations not designed for such concentrated spikes. By disabling a single charging node, thieves turn the remaining EV fleet into an unintended stress test for local grid stability. The Cybersecurity and Infrastructure Security Agency classifies these thefts as a systemic vulnerability with the potential to trigger cascading failures across transportation and energy sectors. Emergency personnel can identify hazards by looking for frayed cables, cracked connectors, and broken insulation that exposes the wiring. To assist investigations, manufacturers often mark cables with identifiers like property of Tesla Motors, or use theft deterrent systems that release dyes when a cable is tampered with. Immediate response relies on authorized personnel locating the emergency shutoffs to disconnect power. Bystanders should document the scene without disturbing it. Sustaining a reliable national network requires active defense against these specific vulnerabilities, ensuring that a series of localized crimes doesn't compromise the stability of the entire regional grid.